thanks a lot to all of you for being here, and to the organizers for organizing this event, and for giving me this very nice opportunity of presenting my results. These are results actually in collaboration with Francesco Buscemi from Nagoya University, Sorko Shiba from Waseda University, and some students of mine. This is a series of work actually. So while we wait for a few more people to join us, just a couple of words in the motivation of this works, series of works. So the quantum guesswork, as the name maybe suggests, is a quantifier of information, and it's perhaps unknown to most people. It's kind of new in quantum information, even though it had been studied quite a lot in classical information for like a few decades now. And this is kind of surprising because, like, as I will show in a few slides, in the classical case, the problem kind of trivializes. So I would dare to say that the context in which it is really interesting is the quantum one, at least for what we are concerned with. So being a new quantifier of information, it can be applied to many different contexts. So in this presentation I will talk about how to compute it, but applications include like information disturbance trade-offs with this new definition of information, or Bell tests, or even certification of the security of cryptographic protocols, in which of course you can use other criteria of information have been considered. So you can imagine of replacing this one, or like resource theories, like Lorentz curves and testing regions have been defined in terms of the error probability in the state discrimination. So you can use this new quantifier of information really in plenty of different contexts. But for this presentation we will be mostly concerned with its computation. So the presentation is split in two parts, each of which is also split in two parts. First I will give the main results, so how to compute the guesswork, which is kind of surprising by itself because for various reasons the quantum hypothesis testing is known to be solvable only for the binary case. This is called Hellstrom theory, and in the symmetric case. While here we managed to prove, actually we disproved previous conjectures according to which the guesswork 2 was not solvable. We actually solved it in more general cases for which the hypothesis testing problem is not solved. And we did this by exploiting some inner structure of the problem that I will show you later. And to solve the guesswork, something, I mean, in the process of solving the guesswork, something weird to me at least, emerges. So the guesswork is a linear problem, at the end of the day is an SDP, but it's an NP hard one. So that will be clear in a moment. And it will be, well, basically because the dimension explodes factorially. And it will be recast as a combinatorial problem. I think it's pretty uncommon. I mean, I'd never seen any hypothesis testing problem turning into a combinatorial one. But that way you move from a continuous optimization problem to a discrete one and you solve. Then I will show some applications. Okay, let me start with the formalization. So as always, this contexts of quantum hypothesis testing or related problems, we are considering a game theoretical scenario, a single partite one, in which there are two parties. One, Alice, has an ensemble, and Alice's side of things are exactly the same in quantum hypothesis testing. So she has an ensemble, she picks a classical variable with some probability distribution which is known to both parties, and she gives Bob a corresponding quantum state, also the ensemble, so that the states of this ensemble are known to both parties beforehand. What changes with respect to the usual hypothesis testing is Bob's side of things. So in hypothesis testing, the standard hypothesis testing, Bob can only query Alice once, and his task is to get the state right with minimum error probability. In this case, in the case of guesswork, as the name suggests, Bob can query Alice multiple times, So the classical variable at its alphabet was ABC, Bob can ask Alice, was your state A? If not, was it B? Or whatever ordering he might prefer, until he gets it right. So he can perform many queries. The important thing is that he gets the state from Alice only once. So at each query, I can do some operation like a quantum instrument to the state, and the state will be degraded at each time. So it just gets the state only once. When he gets it right, and they repeat the experiment many times, and we have an average of this guesswork, so the number of queries it takes Bob to get the value of the classical variable right. So the figure of merit, in the easiest formulation, the figure of merit is the number of queries, guesswork, but more generally it can be a function that depends on that. So the function only depends on how many queries it took Bob to get it right. Typically you can think of an increasing function. It doesn't even have to be like that, but it makes sense to think it that way. Okay.
Sorry, can I ask?
Sure, of course.
So at different rounds, the classical state can be different.
So at each run of the experiment, the state is both the classical variable and its corresponding quantum state is picked from the ensemble with the probability given by the ensemble. But Bob he obtains only one copy of the state until he gets it right. So I will show it in a moment what the most general strategy is, but it's clear that the most general thing he can do is to perform an instrument that gives him one value. He queries Alice for that value, and if the answer is on the negative, so if he didn't get it right, he can use the output of the instrument, so the state he obtained initially degraded by the instrument, to perform another instrument, get another outcome, query Alice again, and then again, and then again. So he has one copy that he can use, only one copy, until he gets it right. Then they start again. I have the most general strategy in a couple of slides. Okay, so just a little bit of notation. We will consider finite dimensional Hilbert spaces, the ensemble to be also finite. M is the alphabet of the classical variable, H is the finite dimensional Hilbert space, and E, calligraphic E, is the set of ensembles, so just subnormalized states. So the ensemble carries the information about the states and the probability, and this is known to both parts. Okay, so like I said, the most general thing that Bob can do is a sequence of quantum instruments. So he gets one copy of the state from Alice. Quantum instruments are represented by, again, in the finite case, by families of completely positive maps. Hilbert space can change, so the input can get bigger or larger, whatever, whose sum is trace preserved. So they are the most general representation of a non-demolishing quantum measurement. Non-demolishing because Bob might get it wrong at the first time, so he might need to perform another measurement, and so on and so on. So with I will denote instruments, the set of quantum instruments. So the most general strategy that I promised is this one. For each run of the experiment, Alice has this classical variable and sends the corresponding state to Bob. Single wires are, I'm using the standard notation from Nielsen and Chang. So single wires are quantum systems, double wires are classical systems. So Bob performs an instrument, I1, gets an output, and queries Alice for that output. This equal here means that Alice is performing a comparison, and say the outcome, the outcome of this comparison is no, so Bob didn't get it right. So Bob will perform a second instrument and a third instrument until he gets it right, until the classical outcome of the instrument is the same as the one Alice had. Okay, just the naive, most general strategy that he can do. So we can write with like Q the probability of success at the tth query, the query number T. So it depends, of course, on the ensemble itself given by the problem, but it depends also on the strategy, this tuple of instrument that Bobs decide to perform. And if we do so, then the guesswork is just the average of the cost function gamma. The cost function, like I said, it only depends on the number of the query at which Bob gets it right. In the simplest case, it can be just the identity function. So Bob pays $1 if it gets it right after one query, $2 if it gets it right after two, and so on. Or it can be also seen as the time it takes him to get it right. So the guesswork is the average of this function averaged over the probability of getting it right at the teeth guess, just this expectation value.
Can I ask a question?
Of course,
for
please.
your previous slide.
Yes, sure.
So just to, in principle, this looks like an interactive scheme, but he could just continue doing it, and at the end, take, whenever he got the yes in between, right? So.
That's what I was about to show in the next slide.
Oh,
so
sorry. Just try to understand what's
no,
going
thank
on.
you. You're perfectly right. So the feedback from Alice is irrelevant, because even if Alice says, I think this is what you were.
Yeah, I mean, she says he
Yes,
just goes on,
he
and
can.
if there had been a yes somewhere.
Precisely. Bob can go on anyway, so he does not have to stop. And well, I was about to show it, but if we do that, then all the instruments basically collapse in a single instrument.
Mhm.
And in particular, we don't care about the final state, so we can trace it out, so it becomes a POVM. And importantly, this POVM produces as outputs not anymore letters in this classical alphabet, but tuples of letters. Okay, so we move from, so here we have many irrelevant degrees of freedom. I think this was basically your observation, and this is not really tractable analytically. But if we do that, observe that the feedback from Alice is irrelevant, and then we can compress all this sequence of instruments, then we have like a big POVM in this sense that is more tractable. But before going in that direction, I want just to say that the minimum guesswork is the minimum over all, naively speaking, all instrument strategies of the function I showed before. So this is just the definition. And then your observation. So we define numberings of these alphabet. They are basically just permutations of, or tuples without repetitions of this classical alphabet. And we consider POVMs that are numbering valued. So POVMs, we move from many kind of simple instruments to a single POVM, which is a mess because it has factorially many outcomes, and each outcome is actually a tuple of letters in M without repetitions. So except for this labeling, it's just a POVM. So the fancy thing here is that there are many outcomes and they are tuples of letters. And then Bob will query these letters in the order given by the tuple until he gets it right. If we do so, then the strategy becomes this one. So you see only a quantum wire here. Bob gets his quantum state unknown to him, performs this super huge POVM that gives him a tuple. That's why I wrote it in boldface, because it's not a single label but a sequence of them. Queries Alice for the first element in the tuple. If it's right, if it's wrong, then it goes on until he is right. But he got the entire tuple from the very beginning. So the strategy becomes, the quantum part is only at the very beginning of everything. And we got rid of many irrelevant degrees of freedom, and this is more tractable. This is the first observation. And well, if we do so, the guesswork becomes the average of the cost function, average with respect to the probability of winning at the teeth query, probability that depends on, again, on the given ensemble, and the strategy on Bob's side at this time is a POVM. So pi here and in the following will denote this numbering valued POVM. So the difference with hypothesis testing is that in hypothesis testing your POVM has as many outcomes as the states. Here it's completely different. There's factorially many more outcomes that are tuples of the letters of this alphabet. Of course.
You still allow some form of adaptation of what Bob asks. based on Alice?
Well, I think the observation and also this quantum circuit shows that without loss of generality, you don't need to do that. I start from the very general setup in which this could happen for the sake of generality, but then we can observe that the feedback from Alice is irrelevant because the feedback can go two ways. No? If the feedback is no, you go on with the optimal strategy. If the feedback is yes, you can do whatever you want. So why not? We still go on with the optimal strategy. So we have a single sequence, optimal sequence of instruments, irrespective of anything that we can get from Alice in between. And then we collapse it, we trace it at the end, and that becomes a huge POVM.
You need to at least adapt to whether you continue to ask questions or not. Because you're trying to do this.
Well, you don't need to adapt it because here I stopped the circuit at the yes, but I could have written the rest of the circuit. Bob would still be winning at number T. Whether he queries Alice, actually queries Alice or not is up to him, but he can perform all the instruments without loss of generality. This is was proved. This is not a result of mine for at least for the trivial cost function. The identity cost function was proved by Wildy Datta. I'll have some references at the end, and some students of them, and we generalized it to the general figure of merit, but I mean the generalization is trivial, so the result is theirs. Okay, so thank you for your question. I think the point is this, that the feedback is irrelevant. So we allow for it at the beginning for the sake of generality, but we don't really need it. So POVM strategy, single POVM strategy with many outcomes, factorially many outcomes, which is why the problem, even though on SDP everything is linear, it's NP hard. I mean, that's not a proof, but we will prove that it is, and the main reason is this, that the size grows factorially. So I was here, and here we have the lemma that basically summarizes your observation that the POVM strategy is as good as the apparently more general quantum instrument strategy. So without loss of generality from now on, we consider the single POVM, which is numbering valued. Okay, so from this point on, I will state the main results. So this was just the formalization. If there is any other question about how the problem works, maybe this is the right time. Okay. So maybe you have already started seeing that this is a combinatorial problem. So basically we are assigning values attained by the cost function to states of the ensemble. Even if you have not noticed this yet, this lemma tells you that this problem is covariant under permutations of the ensemble. The way I defined it, the ensemble doesn't even need to be ordered anyways, and also permutations of the values attained by the cost function. So like I said at the beginning, it makes sense to consider a cost function, operational sense, to consider a cost function that is increasing in T. The more players it takes you to get it right, the more you have to pay in some sense, but it's not strictly necessary. You can permute it, and the optimal solution will be permuted as well, and the value attained will be. Okay, this is not very deep, just to emphasize the combinatorial nature of the problem. Okay, then we can, I promised you already in the subtitle that this was hypothesis testing, but so far it's a different problem. Well, if we define these operators E, which are just linear reshuffling of the states of the ensemble with weights given by the, not linear, I mean, at the end of the day will be a affine function, but weights given by the cost function, we can reframe the guesswork as a state discrimination problem. This is the affine redefinition of the problem. So I call it a state discrimination problem, a quantum hypothesis testing problem, because we have a single index that grows factorially in the size of the classical alphabet. These are our POVM elements, the POVM elements that we have shown to be completely general. And now we are doing discrimination of these operators E. They are not states, they are not positive, they are not unit trace, but typically the techniques that we use in hypothesis testing do not depend on those properties of the state. So this is just an SDP that can be solved. The thing is that the optimization space grows factorially, so it's an NPR in this sense. I'll prove that it is NPR in a moment. So we want to say something more. We want to solve this, and what do we do? Well, first of all, we have to restrict. This is just a technical restriction. I cannot help having it. To balanced functions, cost function. A balanced cost function is just a cost function such that for any value it attains, there is another value such that the sum of the two is the average of the function. The identity function, so you get it right at the first time, you pay 1, you get it right at the second, you pay 2, and so on, is balanced, of course, but it's not the only one that is balanced. And if the cost function is balanced, then you have this property of these pseudo states you are trying to discriminate. So for any pseudo state, for any of these operators, they play the role of states, if you want to see this as a state discrimination. In your new set of states, there is also its opposite operator is also present in the set somewhere. Okay, and this makes it so that this object over here is a POVM. It wouldn't be otherwise. So I define a POVM. The POVM depends on the data of the problem, so the cost function, the ensemble. It depends on a numbering, a permutation of the letter of your alphabet. And this POVM is actually a test, a binary POVM, because all the POVM outcomes are 0 except for 2, and it's a Hellstrom-like POVM. No, because the two effects which are not null are actually given by the projectors on the negative part of this and the negative part of the opposite, so that the positive part of this one. Remember that this object for n star and this object for n star with this permutation are opposite in sign. So this is a Hellstrom POVM. And the logic here, maybe I can give some quick intuition if it helps, is that we have these operators E that we want to basically to discriminate, and they are traceless if the cost function is balanced. So I can draw them in the hyperplane of traceless operators. So let's say one is here, this is here, so one is here, and then there must be the opposite one over here, and then one is here, and one is here, and so on. And one is here, and maybe one is here. So if we use the duality of the SDP problem that I wrote a couple of slides ago, then our problem consists of finding the operator that majorizes all of them and that is minimal in trace. So basically we have to find the cone whose vertex is somewhere here that majorizes all of them and that is like lower in some sense. Okay. By central symmetry, this cone will be centered on the origin by central symmetry, because these are for any E there is minus E in the set, and therefore we will only want to distinguish the two operators E that are further away from the origin. Okay, and we will discard all the other ones. This is an intuition of why this POVM is optimal, and this fact is formalized by this theorem. So that POVM, that test, that Hellstrom-like measurement is optimal whenever you can find an n star, a numbering, such that these conditions are verified. Okay, what is the logic, the relevance of this statement that we are recasting? And if that is the case, then this is the guesswork. We are recasting the guesswork problem, which is an SDP. It's a continuous optimization problem, as a discrete optimization problem. So you have to verify these conditions for all numberings. The numberings are many, they are factorially many, but they are finite for any given problem. And if those are verified, then you are done. So we are moving from a continuous optimization to a discrete, actually combinatorial optimization. So you might say, okay, these conditions maybe are academics, they who cares about them, maybe they are never verified by any interesting ensemble, so that could be an objection. I will answer that objection in the next slide. For now, is it clear? If there is any question about this main result, it's...
So this is the perfect value then, right?
Yeah, if you find
the
an...
second formula is also very helpful, right? Because it tells you what the optimal value is.
Yeah, if you find an n star such that this is verified for any n, so you search over factorially many things, and for each of them you have to test factorially many conditions, but at least they are finite. Then you're guaranteed that
Then you're done.
you're done. Yeah, the P of M I showed you in the previous slide. The test is optimal, and it's just one line to show that the guesswork is given by that.
Is this a necessary condition for optimality?
For the optimality of that P of M, I don't know. Okay. So if this is clear, then I think the objection could be are those conditions purely academic, or are they interesting in some real-world application? Or even more, stronger statement would be, I mean, we can solve the hypothesis testing problem, like I said at the beginning, for the binary case, ensembles of two states, that's Hellstrom, or for the symmetric case. Can we use those conditions in situations other than those two? So can we solve the guesswork problem in situations for which we cannot solve the hypothesis testing problem? The answer to this was conjectured to be false, but it is not. To show that it is not, just a little bit of additional notation. Gram will denote the gram matrix of a function. X will denote a permutation matrix, and with V I will denote the Pauli vector. So the decomposition of any qubit density matrix on an orthonormal basis on the space of traceless operators. Okay. If we do that, then we can prove that for any qubit ensemble, those conditions are verified. There exists an n star that satisfies those conditions in the theorem I gave before. So for any qubit, this is not constructive, so I cannot tell you what the n star is. Still, you have to look for it in a factorially growing set, but you're guaranteed that it exists. And so that test is optimal. So for the qubit case, it is convenient to rewrite the problem in this way. So this is the same thing I wrote before. You have the gram matrix of the values attained by the cost function. So this is an outer product of the vector of such values. These are permutation matrices, and this is the gram matrix of your qubit ensemble. It is important to rewrite, it is useful to rewrite the problem this way, because this is how quadratic assignment problems are framed. So maybe at the beginning I also mentioned that I was going to introduce some classical combinatorial result that is maybe not, I've never seen it applied in quantum informational problems. Maybe you have, I don't know. And this is exactly what I was talking about. So a quadratic assignment problem. Quadratic because it's a quadratic function of your variable x, and so we are optimizing over permutation matrices. And assignment because we are assigning vectors in the ensemble to values of the cost function. And this is yet another way of writing the guesswork in the case. So this is called quadratic assignment problem. It is known since it was called that way and studied since the 50s, and the results we use are mostly, write that, so let me write this here, by Cela and collaborators and it's a corpus of works that date back to the 90s, I would say mostly, on quadratic assignment problems. Okay, so we can always, for any qubit ensemble, we can always move from a continuous optimization problem to a discrete one, a combinatorial one. So in some sense, this is in this sense, this is a closed form solution. But still, I mean, it's an NP-hard problem and a search over a factorially growing set. So what can we say more than that? Are there situations in which we can solve this NP-hard problem? QAP is known to be, quadratic assignment problem is known to be NP-hard in general. Yes, there are two scenarios that we can address. In one of them, we can have like fully analytical solutions, and this is the case of benevolent ensembles. So benevolence is basically the intersection of what is known about QAP and what is relevant in the context of the guesswork. So what is benevolence? Benevolence is a property of a matrix. I had never heard of it before studying this set of works. So, okay, it requires a matrix to be symmetric, tuplet, and having these two properties. I will not try to give an intuition. They are properties that require some sort of regularity about the matrix. And we call benevolent an ensemble whose gram matrix is benevolent. So the definition, at least for the case of matrix, that the choice of the name is not mine, at least for matrices. So I will not try to give an intuition of what benevolence is, but what I want to stress, I think it's important, is that benevolence is not a property that is not invariant under permutations of rows and columns of the matrix. So benevolence for an ensemble implies an ordering of the states of the ensemble. Okay, and since benevolence implies a ordering of the states of the ensemble, I can define another ordering, which is this one. I call it with a subscript dv benevolent, with respect to the ordering in which the ensemble is benevolent. Okay, so if 1, 2, 3 is the order in which the ensemble is benevolent, and that is given, then I can define a new ordering of the ensemble, which is this one. And why this is relevant? Well, I told you a few slides ago that the candidate for optimality, that P of M that I showed you earlier, actually was a family of P of M that depends on a numbering. And that P of M for this numbering is optimal for any benevolent ensemble. This is the main result. That
will it be triplets after you renumber?
Sorry?
Will it still be a triplets matrix after you renumber?
Sorry?
So you have this, the Graham matrix of row is triplets, and you'd like to renumber it?
So the Graham matrix of the ensemble is cardinality of M times cardinality of M matrix, and of course you can permute rows and columns, which corresponds to permuting the states of the ensemble, and the benevolence is not invariant under these permutations. So if you can find, and you can do that in polynomial time, a permutation in which the matrix is benevolent, then with respect to that permutation, this ordering over here gives you the optimal P of M.
But if the original Graham was triplets and you renumber, it won't be triplets. So you're asking if there exists a renumbering that makes the Graham matrix triplets and this increasing property.
Okay, I don't know. I haven't thought about it.
Okay, sorry.
So for us, the relevant property is this benevolence. That is enough to guarantee the optimality of the P of M corresponding to this ordering. Okay, and this is stated by this corollary. So if you have a qubit ensemble whose matrix is Graham matrix is benevolent, then you are done. And if it is, if there is a permutation according to which the matrix is benevolent, you can find it out in polynomial time. This is somewhere in here. So benevolence is enough. Okay. Okay. Final, second and final application is. Since it's a combinatorial problem, another approach is to use is algorithmic. No, so you can apply an algorithm, and the problem is finite, so you can get the exact solution in finite time. Oh, sorry. Before saying that, this family of ensembles, so the ensembles whose representation in the block sphere is like rotates on the equator and bumps up and down, so they are anti-prismatic, no? Because this is something that's moving on the equator, and this goes up and down. So they are anti-prismatic, and what we show is that they are benevolent. And they are important because they include regular polygons, they include the tetrahedron, the SIC, they include the octahedron, the SIC being the antiprism whose faces are two vertices, and the octahedron being the case for two faces with three vertices each. They are benevolent as long as the h, the height of the prism, is not too much, and actually when these bounds are saturated, you have the uniform antiprism. And under those conditions, we show in this corollary that the ensemble is benevolent. So basically, all important ensembles you can think of are, important for applications. Like SICs or MUBs, things with a name, they are typically benevolent. Okay, then like I was saying, there is another approach you can follow, which is the algorithmic one. The problem is combinatorial, is finite. So if the input is exact, like you can write your ensemble on a ring, on a discrete ring, or something like that, which is what we do, then you get an exact result, exact guesswork, and P of M attaining it in finite time. Typically in this quadratic assignment problems, what is used is a branch and bound algorithm. This is also something I was not familiar with before studying this, so I'll briefly mention what they are. So you have an optimization over a feasible set of solutions, and this set, like I said many times, is big because it grows factorially with the size of your original problem. So if your ensemble has say 30 states, this number is more than the age of the universe. So you need to do something smart. Branch and bound algorithm do the following. So at each step they branch, so they partition the optimization space, the space of feasible solutions, and for each subset they compute a bound, and if the bound is good enough for some of the subset, they can say, okay, this subset will never give me a solution which is better than the best solution I found so far. So this is the logic. So you need a good bound in the sense that it must be as tight as possible, but also quick to compute. So there is basically a trade-off in this respect. Okay, and here I give a branch and bound algorithm. Maybe I will not go into too many details, but basically what I do is I give the objective function. You have seen this also in some of the previous slides. The optimization space in its trivial version is just the set of all orderings of my classical alphabet, and then there is a branching rule and a bounding rule, like I said. And using this algorithm, you can show that you can improve over the naive algorithm. So the naive algorithm would take cardinality of M, cardinality of your classical alphabet, factorial, many steps. So there are that many numberings for which you have to check the conditions that I've shown before. However, because of this pruning of this tree, because of this bounding that I mentioned, this is just an upper bound. plus in the presence of symmetries. So if my ensemble is invariant under the action of a group that is transitive, or if the ensemble is centrally symmetric, we can do better, and we can do better by a factor that is the best case, the presence of both symmetries, which is quadratic, and might not sound like much given that the problem scales factorially, but well, it allows us to a bit further. Okay, so with this approach works like that. So in the general case, you have to build to consider all the permutations of your classical alphabet, say A, B, C. So you can represent it as a tree. First you fix the first letter, the second, and the third one in all possible ways. If you have transitivity, it doesn't matter what is the first letter you fix by definition of vertex transitivity of your ensemble. And so you can fix A and proceed as before. In the centrally symmetric case, it's a bit trickier, but you can prove that if you fix one letter to be the first one in your tuple, in your ordering, in your list of queries to Alice, then the letter which corresponds to the state which is opposite to this one needs to be the last one. And if B your second is your second letter, then the letter corresponding to the state which is symmetric to B needs to be the second from the last one, and so on. Sorry, this is a typo. This should be an A bar, and so on. So this is why you get a speed up from factorial to doubly factorial, which corresponds basically to a square root speed up. And you can have also both things at a time, so the speed up for the transitive and centrally symmetric case that are multiplicative in this case, so we got lucky. Plus the problem, didn't mention that, but scales well if you run it in parallel, so it can just be split over C cores of computation, and the speed up is the best you could hope for. So if you do that, well, you can push the algorithm quite a lot. There is this class of ensembles that was introduced by Zlomczynski and Simusiak a few years ago. Actually, they introduced that for POVMs, but I mean, the same symmetry applies to ensembles. They are called highly symmetric and informationally complete, and in the qubit they correspond to the Platonic solids plus a couple of not that famous polyhedrons, the cuboctahedron and the icosidodecaedron, and remarkably this one has 30 vertices, so applying the naive algorithm would take more than forever because it's factorial. However, we managed to do that and to compute the guesswork of everything, include this guy here with 30 vertices, and like I said, the algorithm is exact, so you get the value. I said this guy has 30 vertices, so if you try them at random with equal probability, so at random it takes you like 15, or by the way the function is defined 15 and a half, because from 31 to from 1 to 30, and it's the average. So guesses on average to get it right, but the minimum you can achieve is something around n.5. Okay, I'm a bit early, 10 minutes early. So let me conclude. So we introduced these, we actually didn't introduce. I have one more slide with references, so we were not exactly the first ones to consider the guesswork in the quantum case. But I mean, we investigated how to compute this quantifier of information that is alternative to other better known ones, like error probability in the state discrimination and so on. And it can be used, it can have many applications, like anytime you can think of an information, now you can think of replacing this one. So in information disturbance trade-offs, certification of cryptographic criteria, resource theories, like I'm thinking of like redefining things such as Lorentz curves or testing regions in terms of the guesswork and so on and so forth. So this is what you have, and it's very easy to see that it is actually an SDP, but this is very much not the end of the day, because it's an NP hard one, because its size grows factorially, and actually that is beginning of the problem. So you can show that what we have shown is that you can recast it under certain conditions as a combinatorial problem, and that this combinatorial problem actually, it is always recast as a combinatorial problem for qubits, and this problem is called in that case the quadratic assignment problem. And we discussed applications, so we showed that the intersection of what is known here and what is relevant for us is benevolence. For benevolent ensemble, you have the optimal solution with complexity 1. And for those ensembles that are not benevolent, you can still apply algorithms that are well known in this context by properly, suitably choosing your branching and bound functions, and we applied that to highly symmetric ensembles. Okay, this is the very last slide. So this list, to me, to the best of my knowledge, is exhaustive for what concerns the quantum guesswork. Like I said, the guesswork in the classical case was studied since the work by Massi in, I think, '94. Just one word on the classical guesswork. In the trivial case, not the trivial, I mean, but in the simplest case in which there is no side information, you just guess the states in the decreasing order of their probability. Even if there is side information, but that information is classical, so in this language it would be like saying the states of the ensemble are pairwise commuting, then the problem is still trivial, because in that case the only so without loss of generality, also your P of M will be on that basis, and the only extremal the problem is convex, it's linear actually, so the optimal P of M will be extremal, and the only extremal P of M over there is just the von Neumann on that basis. So the P of M is given trivially, and the labeling associated to each P of M element is also trivial, because your P of M gives, through Bayes' theorem, gives you a posterior, and you will query Alice for the states in the decreasing order of their posterior. So the guesswork problem, computing the guesswork problem is trivial in the classical case. There are still many things that have been said, like relations with Renyi entropies or proof of the of entropic properties of the guesswork itself, but computing it is trivial. So in the quantum case, it was introduced, to the best of my knowledge, in that work over there a few years ago, and then studied again by Dutt and Wilde more recently. And I have to say that this presentation is based on these two works, but this series of works of ours on the topic originated by a conjecture that Eric, the first author of this work, had and shared with me during a visit to the University of Cambridge before the so, okay, this is it. Thank you very much for your attention, and I hope you have questions. Thank you very much.